So we want reactions at A, B, the pins, the external pins, and C, that internal pin. And we are told that this cylinder has a mass of 80 kilograms, and we're in static equilibrium. Identifying it as a frames of machine type question, I recommend then skipping that external free body diagram, since we know there's going to be at least four unknowns in it, because A and B will each give us 2, and jumping right into drawing the individual members and what's happening on them. I would recommend actually not separating out member AD from the pulley. I would keep them together, and then we will not see what the pin forces are at D. If I draw member BC, I'm separating it from a CD, and I'm separating it from the wall at B. I'm going to have one applied force acting on it. At this point, put in the amounts here. At the right end of this, it's attached to the rope. I'm not including the rope in the picture, therefore I have to include what the rope does to what I kept of BC. The rope can only pull, so it must be pointing up here. It must be pulling on that right end of the member BC. And because it's one continuous rope that goes over the pulley onto where that mass is, and we're in equilibrium, the tension in the rope is constant, and I know that that tension is going to be equal to the weight of the cylinder. Since it has a mass of 80 kilograms, I can find its weight by multiplying by gravity, and that's going to be about 785 newtons. That's the applied load acting on it. Where I disconnect it from the wall at B, I have a pin. I can decide then to have a BY and a BX. And at C, I have that internal support. It's pinned to my other member, ACD. Because ACD is not in this picture, I have to model what ACD is doing to BC. Just like we saw before with our internal pin connections, it's going to act like an external pin, but it's going to be different when it appears in my other picture. I have CX and CY from that internal pin connection then too. There's 4 things I don't know in this free body diagram. My second member, I'll show you kind of the alternate way we can do this, but a little bit more efficient way to do this one is I'm going to keep together that member ACD and the pulley in my picture. Because they're together, I don't see what's happening at the pin at D, and we'll see how that affects this version of it versus if I did a different way to solve this. I know that's 1 meter. That's 0.5 meters. And this is another 0.7 meters. Okay. Actually, that's 0.7 to the left side of the pulley. And then on the pulley, we have a radius of 0.1 meters. I'm keeping together ACD and the pulley, so I'm going to put on the effects from everything I did not include. At A, I removed it from the wall and from the pin that was attached to the wall. I have to have that pin reaction, AY-AX. At C, it was internally connected to another member. Because in my first picture I said CX was right, CY was up. This is where I have to make sure that they're pointing in opposite directions. So a CX left, CY down in this picture. If you said down and left in this picture, I would do up and right here. And you're going to get the same answers either way, just the signs on C will be reversed. But as long as you're consistent with the picture, that's going to be what matters. Now I have to contend with the pulley, or the rope that was going around the pulley. One way to imagine what's happening is I can actually, in my picture, include some of the rope and then cut through it will be one way to imagine what's happening. So I'm only including the top part of the rope as part of my object. So where I cut it, I can see what the tension in the rope is. And we see because we're cutting through two sides of rope, I have two tensions. I have the tension from the right part of the rope of 785, and I have the tension from the left part of the rope of 785 newtons. I can't see what's happening at D because it's still pinned together. The pulley is still attached to that member there. In the alternate one drawing I could make, then I can see what's happening. But if I keep them together, these are all the things that I'm seeing here. The AXAY, the C, and then the two sides of the tension. Had we separated out the pulley from member ACD, A would look exactly the same. I won't draw these in full, but just to get a sense of what's happening. We have that pin at C. And if I don't include the pulley still attached, then I have to include what was the pulley doing to member ACD. In this case then, because they're pinned together, the pulley can rotate around that pin. In this picture, I would include at point D a dx and a dy. Here the tensions don't act through point D, acts to the left and to the right. I'm assuming point D is the center of that pulley where the pin is. But in this picture, the pin itself does act at point D. Had I used this picture and the first picture, we see we have 8 unknowns because dx and dy we can see when I separate off the pulley. Which means if I have 8 unknowns but I can only get 6 equations, I would need another free body diagram in order to have enough. Right? So I will need also a picture then of the pulley. So at D I have the opposite effects here. And then the pulley is seeing these tensions on the side of it. So this would see the 785 on the left and the 785 on the right. Between these 3 free body diagrams then, I would have enough equations to solve for my unknowns. And the additional information I would get is what is the force on the pin at the pulley, which for the purposes of this problem, we don't care about. So if we can have a method that doesn't solve for them, that's okay. Like in other problems where maybe it's enough to only have 4 equations out of the 6 to get what we need. We don't need those other 2 equations. We could solve them and get more information, but we might not require it. So we can either have picture 1 and picture 2, or 1, 3, and 4, or actually all 4 of them to get our solution. If we don't use 3 and 4, we can't find out what dx and dy is if we're concerned about what they are. But we'll get the same answers in any combination that we used. Since there's 6 equations we need to write, because we have 6 unknowns, we can choose any one to start with. But if we're solving by hand, which one is going to look like the easiest equation to start with? We can start with either free body diagram, we could do a moment first, we could do a force first. If we look at free body diagram 1, basically if we're doing it by hand, we want to try to get equations that have only 1 unknown if possible as our first couple equations. That's not always possible, but here it is. If we look and start in picture 1, if we take the moments around B, that will leave us with only 1 unknown in the equation, Cy. If we looked at free body diagram 2, if we took the moment around A or C or D or any of those, it will always give us at least 2 unknowns in them. So in terms of starting, I would say starting with the moment around B is a good place to begin. If we look at that, we do have just 1 times Cy, and that's going to be counterclockwise around B, plus 1.7 times 785. And by starting here, we can find the value for Cy right away. Because in this picture I drew it up, I got a negative 1330 newtons. Again, looking for equations that only will have one thing we still don't know. Where can we go next in these series? Right? So same picture. If we sum forces in the y, since we know Cy, By is the only thing we don't know. So By, I get 550 newtons, and that's up. That's one piece of the reactions that we're looking for. And while I'm here, still thinking about free body diagram 1, I might as well get the last equation. Two unknowns in the one equation I have left. So it does tell me Bx is negative Cx, but I'm going to put this aside for the moment and then come back to it once I have more numbers. I know 2 numbers of the 6. 3 I'll come back to then. Right, moving on, based on the 2 numbers I know, where can I go to next to get equations? Right, one option would be, free body diagram 2. If I sum forces in the y, Ay will be the only thing left that I don't know. So that's a good next one to do. I get Ay minus Cy minus twice 785. Because in this picture, I have both sides of the tension. Again, I would just keep reiterating that internal connections C have to have the equal and opposite directions in the first picture it appears in and the second. Otherwise, I could get Cy correct, but if it's in the wrong direction in my second one, it's going to give me the wrong answer for Ay. So based on this directionality minus Cy, then putting in the negative 1330 for Cy, I get that Ay is 236 newtons up. Right, so I can do a moments equation now in picture number 2. Now if I sum moments around A, I do have Cx and Cy in it, but I already know Cy from that first equation that we encountered. So the sum of moments around A is going to give us 0.5 times Cx minus 1 times Cy minus 785 times 1.7. You have to be careful in the dimensions in this one. The left side of the pulley is 1.7 meters to the right of A, minus 785 times 1.9, the distance to the right side of the pulley. Because I know Cy, I can find that Cx is 2980 newtons. Since I know Cx, I now can come back to equation 3 and find Bx is going to be a negative 2980 newtons. So that's pointing to the left. Finally, if I sum forces now in the x direction in picture 2, I have Ax minus Cx, and that will tell me that Ax has a value of 2980, and that's to the right.